I hope you can hear me.
Yes, ma'am.
Yeah. I hope you are all safe. Your families are all safe. Your parents are all safe.
Yes, ma'am.
Yeah.
Yes,
Be
ma'am.
very careful, please. Just now we got the news of the death of one more member of ICFI family, not from FST, but from IBS. Just few days back, we had another person. So many. It's very pathetic. Very shocking. It is. Please, all of you, take care. Don't put your family to risk by going out unnecessarily. Okay? It's a very humble request to all of you. In fact, my husband and I, we were down with COVID, and we are so thankful. We are so thankful to, I don't know, to nature or to God, or I don't know what I must say, but then we are so thankful that we are alive and it didn't become serious. In fact, I have my 84-year-old mother staying with me. She is also safe. That is, she didn't get it. That itself is a big boon for us. So all of you kindly take care of your parents. Okay? And youngsters are also not spared. Please understand that. And for your own safety, for the sake of your parents, all of you, be careful. Okay, this is all we can say now. Okay, so let me start. The typical values of, I was talking about the shanty dog the other day. How many of you remember that? Anyone? Nobody remembers? Shanti ante Santa. Are you able to remember it now? I don't know what to do with you guys. Only God can help you. Okay, so I told you that how a metal will look. If you can see atoms, this is how it's going to look. The positive ions will all be fixed to their places. In chemistry, you have talked about, you have studied about simple cubic, you have talked about body centric and all that, right? BCC structure, FCC structure. So accordingly, the atoms will be going and sitting at those places, and your electrons, 1 or 2 electrons of each atom will be free. It will break free, and they will be free electrons and not localized to any given atom. And what happens to these free electrons? The free electrons will get energy from the temperature. Temperature is energy after all. So it gets energy and it will be in a state of constant motion. In random direction, they will be moving. And in moving, what happens? When they move, they will hit against. Hit is a very crude term to use. They don't really hit. There is something else that will happen that I'll explain later. So, but they hit against the lattice. Lattice are those positive ions, and then lose energy. Lose energy, and then the direction changes. Then again it hits, then again it changes direction. So that way, it's just like, it is just like a dog walking around in a shandy. It doesn't reach anywhere. It just keeps running around, and it is not actually buying anything in the shandy. But then what is the speed at which this is happening? This is happening at a speed of 10 to the power of 6 meter per second, which you know is very large. Now, I should take you back to what we had discussed in the previous class about current density being related to something called the drift velocity. We saw that whenever you are applying an electric field, then there is a current in the direction of electric field. The current density is related to the number of charge carriers per unit volume and the average speed with which they will drift in a direction opposite to the applied field. Okay, and that equation was J is equal to minus NE VD. VD is called the drift velocity. Now what we are going to see is what will be typical value of drift velocity. What will be the typical value of drift velocity? That we'll see in a few minutes. But before that, let us look at this problem. This problem says that, you have an aluminum wire. You have an aluminum wire, and this wire has got a diameter of 2.5 millimeter. It is welded to a copper wire. It is welded to a copper wire. Okay, and it's also shown that this copper wire is going to have a dia greater than that of aluminum. Okay, so I'll say that dia of aluminum is 2.5 mm. Dia of copper is sorry, I should have told the other way. Dia of copper is 1.8 mm. which means if I have to draw a picture, I will show it like this. This is your aluminum. And then let me show my copper. Copper is thinner, is going to be like this, and these two are welded. These two are welded. Okay, so this is copper. Now, what is asked is, what it says is the composite wire. Composite wire means a combination of these two carries a current 1.3 ampere. So there is a current of 1.3 ampere entering. So what will be the current that is coming out?
1.3 ampere.
Right. What comes out also will be 1.3 ampere. Okay. Now you have to find out what is different between these. What is going to be different? If the current is going to be the same, what is going to be different in these two wires? So for that, he's asking you to find out the current density in each wire. What is current density? Anyone remembers? Current density is current divided by
Area.
Okay, so I will say pi d, diameter of aluminium, by 2 will give you the radius. So pi r square will give you the area of cross section. So if I substitute the values, I am going to get the current is 1.3, then divided by pi, and then dia is 2.5 mm. So 2.5 into 10 to the power of minus 3 meters divided by 2, that is radius whole square. Okay, if I do this calculation, I will get 26 ampere per. Okay, so here he is doing it in centimeter square and giving you. Therefore, it is, but I should give it in meters. So it will be 26 into 10 to the power of 4 ampere per meter square. That will be the answer. Similarly, if I do for copper, by the same logic, I just have to substitute 1.3 divided by pi into dia of copper divided by 2. That gives a radius. So radius square. Make a substitution. You should get 51 into 10 to the power of 4 ampere per meter square. So what do you conclude? So what do you conclude from here? What is your conclusion? Current does not depend on what is the material. Current is not going to depend on what is the material of the wire. Whatever current enters has to come out. That is from conservation of charges. From conservation of charges, the amount of charges entering per second will be the amount of charge coming out per second. But then what is happening on this end? Here what happens is they have a larger area of cross section for the current to go. Therefore, the current density is going to be smaller. But when you come to copper, what happens is the area of cross section becomes smaller. So there is a squeezing of more charges through that small area. It is as if, in a theater, when you're all moving around inside the theater, there is a lot of space. But then after the movie, when you're trying to come out, there is a small door through which many of you have to squeeze in and come out. Okay, so that's exactly how this scene is going to look. So the current density is going to be more once you come to copper. Okay, so you can see here that J of aluminium, current density of aluminium is not equal to the current density in copper. So that's your conclusion. So the current density doesn't really depend on what is the material. It just depends on area of cross section and what is the current. Another thing is we have made an assumption that it is a uniform current, that everywhere inside that wire, the current is uniformly getting conducted. Now we'll do one thing. Now we have to answer that question. What is the typical value of drift velocity? We have to answer that question. Okay. So the question asked is, what is the drift speed of the conduction electrons in the copper wire of the previous problem? So for the previous problem, what did we get? We got J of copper, we got it as 51 into 10 to the power of 4 ampere per meter square. So this was the answer that we had got. So using that, you have to find out what is N. What is N we need, and then from that you have to find out what is VD. You have to remember J equal to NEVD if I'm not talking about it as a vector. Just a number if you're putting, I don't have to put that minus sign. Okay. And what is my E? E is 1.6 into 10 to the power of minus 16 coulomb. Now the question is, what is N? What is N, guys? I'm not asking the value of N. What is N? What is N?
Number of electrons cutting cross-section area.
No. Number of electrons contained, number of free electrons contained in a 1 meter cube block of the metal. Number density. Akshara, it is number density. In 1 meter cube of the material, how many free electrons are there? Because they only participate in the conduction, right? So that is number density. Density always means mass per volume. But here number density. So number of free electrons per unit volume. Unit volume means 1 meter cube. Okay, so we have to find that. For this, I am going to make you go to chemistry. I want to go to chemistry. So N is the number per mole, per meter cube. N is the number of, and please, there is another thing that he's writing. His author says, in copper, you can assume that there is 1 conduction electron per atom on the average. That is, every atom on an average is going to give 1 electron. Let us assume. Then, if I find the number of atoms per meter cube, listen again, if I find the number of copper atoms per meter cube, am I not getting the number of electrons per meter cube?
Yes.
Right. So let us first try to get the number of atoms per meter cube. Okay. You know that the number of atoms per meter cube divided by number of atoms per mole. How many atoms will be there in a mole of any material at STP? Chemistry. Number of atoms per mole of any material will have Avogadro number of atoms. You remember that? Okay, so what we'll do is we'll divide N divided by Avogadro number. And on the right hand side, the same ratio will be assumed by mass also, mass of the copper also. So what do you do? Instead of number of atoms per meter cube, let us take mass per meter cube. And in the denominator, let us write mass per mole. I hope you are understanding the logic. On the left hand side, we are taking the ratio of number of atoms per unit volume and number of atoms per mole. And on the right hand side, we are taking mass per unit volume divided by mass per mole. The ratio will be the same. Okay. So now let us see what these things actually mean. Number of atoms per meter cube is going to be N. Okay. And number of atoms per mole is going to be Avogadro number. And what is mass per meter cube? What is mass per volume? Density. So we write rho m. I hope you're able to see here rho m. Rho till now we kept writing rho as what did we write rho as? What was rho? Rho can be resistivity. So we should not confuse. So he's putting an m there. That m says that it is the mass density, mass per unit volume. That's why that m is there. And divided by mass per mole, mass per mole. What is mass per mole called? Molar mass, right? Mass per mole is called molar mass. Yes, you have your capital M. This you can get from the tables. So now substitute and get N. So N is going to be Avogadro number into density of copper divided by the molar mass. Substitute. Okay. After you substitute, you're going to get a number. This number is going to be very important. N is actually 8.49 into 10 to the power of 28 atoms per meter cube of copper. But since every atom is giving 1 electron, you can simply say that there are 8.49 into 10 to the power of 28 electrons per meter cube. So this is the number density of free electrons. Next, what is there? Nothing. You just have to use it into this equation. J is equal to NEVD. Therefore, we are interested in VD. Drift velocity is equal to J divided by NE. J we already have as 51 into 10 to the power of 4 divided by N, we have it as 8.49 into 10 to the power of 28. Then you have your charge of the carrier. We are not taking about the sign, we are only taking the value. So 1.6 into 10 to the power of minus 19, put everything and you get the answer. You get the answer as 3.8 into 10 to the power of minus 5 meter per second. Is that big or small?
Small.
Very small, very small. If I try to see how much will this translate into distance divided in 1 hour, distance covered in 1 hour, you will find that it is just going to be 14 centimeter per hour. In 1 hour, the electron is able to drift only 14 centimeters. So that means the drift speed is very, very small when compared to another speed that I talked about a few minutes back. What was that speed? Anyone remembers? Dog, shanty dog. What was that speed called? Thermal velocity. You remember? We talked about something called thermal velocity. And what is thermal velocity? Thermal velocity is 10 to the power of 6 meter per second. That's very, very fast. So much of energy. But drift in comparison is very, very small. It is a few centimeters per hour. So that's one point you have to remember. Next important thing that I want you to remember is, the next very important thing that I want to remember is, typically for a metal, what will be the N value? Typically for a metal, what will be N value? It will be of the order of 10 to the power of 28. That number you have to remember. Okay, the number part of it, 8.49, 2, 3, whatever, those things will vary from metal to metal. But then 10 to the power of 28 is going to be the order of magnitude. That remains the same for all metals. So because you have so many charge carriers only, your metal is a very good conductor. Is that clear, guys? Okay. And when we talked about dielectrics or insulators, what did we say in the last class? We said they are insulators because there are no carriers. There are no carriers. So after all, these carriers only carry current. So there are no carriers. So there is no conduction. Whereas here, there are lots of carriers. There are around 10 to the power of 28 electrons in 1 meter cube of the material. So that's the reason why it's able to conduct. So this number you have to remember. Now the next question is, this is a very important question. Now the next question is, if the electrons are really moving at that kind of a slow speed, then as soon as you switch on the light, how is the light on? There is a distance of at least 2-3 meters between your switch and your light. How is it that you are able to, or you switch on the fan, you switch it on here, but the fan is immediately working? When the switch is thrown, why are you able to immediately see, though the speed of electron is so small? Anyone?
The potential difference created drives the electron.
It's true, it is driving the electron, but what is the speed of the electron? It's so slow, no? Why are you able to immediately see it? Okay, the author gives you an answer for this. He talks about a pipe. I'm sure all of you have hose at home. Those of you at least who are staying in independent houses have this hose. You're connecting it to the tap. The hose is there. And when you close the hose here, even if you close the tap here, even if the hose is 10 meters, at the other end, you're not going to see water coming out. Does it mean that there is no water inside the hose? Is there water inside the hose? As soon as you close a tap, is the hose becoming empty?
No, ma'am.
No, there is water. Okay, sometimes if you just lift the hose like this and leave, you can see water coming out. Hose is not empty. But the minute you close it, there is no more water flow. That is because, as she said, there is no potential or there is no pressure difference between this end of the hose and this end of the hose. This end of the hose is at atmospheric temperature, atmospheric pressure. This is also at atmospheric pressure the minute you have closed it. Therefore, there is no no push. Similarly, there is no voltage difference, right? But then as soon as you open it, what happens is there is a pressure variation that you're creating. The water is getting pushed. This pressure variation, that information travels at the speed of light, and from the other end, water comes out. Are you able to understand this? So the water that is coming out is the water that is at this end. So it's able to come out. Similarly, the same logic you take in the case of current, what happens is initially there is no potential difference between these two ends when the switch is not thrown. But the minute you're going to throw a switch, then what happens? There is a potential difference. Potential difference means electric field. You know, there's a relationship between electric field and potential difference. So that means you have applied an electric field. And the electric field went from 0 to a maximum immediately, instantly, went from 0 to a maximum. Or there is a change in the electric field value. And what does the electric field do? You know that F is equal to Q into E. F is equal to Q into E. So as soon as there is an electric field, the charge experiences a force. So this variation of electric field from 0 to maximum happens instantly. And this information also travels instantly through the wire. Okay, so the answer is you feel the electric effects instantly only because information about the change in electric field travel at the speed of light. That's what happens when you have a light traveling also. What is light after all? Light is variation of electric field, a sinusoidal variation of electric field. So variation of electric field travels at the speed of light. The actual electron is, on the other hand, drifting. It is traveling very, very slowly. Okay. Now after this, let's go to the next problem. So the next problem that we are going to see is, now we are not talking of a metal, we are talking about a semiconductor. Okay. So you're talking about a strip of silicon. You're talking about a strip of silicon. Okay. And this is the cross section of the silicon. It has got a width and thickness. Width and a thickness D. So what is the area of cross section? Area of cross section will be width into the thickness. Width into thickness will be the area of cross section. There is a current I entering. Obviously, the same current I will come out. And what is the value of the current? The current is 190 milliampere. And please remember, silicon is a semiconductor. Silicon is a semiconductor. Is it silicon or silica? Silica. Silica is a semiconductor. And you are adding phosphorus impurity and making it an N-type semiconductor. Still, it is a semiconductor only. Okay. And after it is made into an N-type semiconductor, the N, the number of carriers per unit volume is N equal to 8 into 10 to the power of 21 per meter cube. Per meter cube. What does this mean? What is N? Anyone? What is N? Guys, what is N? I'm not asking the value of N. What is the meaning of N? It's all written there. N is the number of carriers per unit volume. In the case of metals, the carriers were what? Electrons or what? Was it electron in the case of conductors?
Yes.
Yes, it is.
Right. Here, what is the carrier? In the case of N-type semiconductor, what is the carrier? +2. N-type also, it is electrons only. What if it was P-type? If it was P-type, it would have been holes. Okay, this is N-type, so it is electrons. Now, what you're supposed to do is find out the current density. So, how do you get the current density? Current density is current divided by area of cross section. Area of cross section, I told you, is width into the thickness. So substitute. So when you substitute, you're getting 190 milliamp. So 10 to the power of minus 3 amp divided by the width is 3.2 mm, make it into meter. Then you have the thickness given as 250 micrometer. So 10 to the power of minus 6 meter. Okay, put everything. And if you do a calculation, you will get 2.4 into 10 to the power of 5 ampere per meter square. Ampere per meter square. Okay. So what you can understand from here is a metal and a semiconductor can have similar J values. They can have similar J values because in the previous problem you had some, what did you have? 54 into 10 to the power of 4 you had. Okay, so you can have similar values of J. So what is the difference between semiconductor and metal you think? What do you think is the difference? Where does
Metal charge carriers are only, but in semiconductors, both holes and electrons can be charged.
but in this case what is carrying? In this case what is carrying? Only electrons. Few holes may be there. Minority carriers will be holes, but we need not even consider them. Only electrons are carrying. What else do you think is the difference between a conductor and this? Do you remember N for the metal? What was the order of magnitude for metal? 10 to the power of? I just told you have to remember 10 to the power of? 10 to the power of? See that and tell me. How much is it for metal? The number of electrons per meter cube is 10 to the power of 28. That is very high. But look at the semiconductor, that too a doped one. What is the value you are seeing here? 10 to the power of 21. That is 10 to the power of 28. So that means around 10 to the power of 7 times you are having more free electrons in a metal as compared to a semiconductor. N is small for a semiconductor. Okay, next. You have to now find out the drift speed. You have to now find out the drift speed. So how do you find the drift speed? Can someone guess what the drift speed will be? So you can see that J was almost the same for both the problems. Order of magnitude is the same, but N here is very, very small when compared to the conductor. And then E is 1.6 into 10 to the power of minus 19. Therefore, you are finding that the drift speed is 190 meter per second. Which is more, for metal or for semiconductor? Hey, if this is the way you people are doing, I'll simply record and just give the material. Why waste time in a class? What is the drift speed in the case of metal? We just did a problem we discussed also. You don't tell me the value, just the order of magnitude. Can you give me? What is the drift speed?
10 power minus 5.
10 to the power of minus 5. That is very, very small. But you come here and see, it is 190 meter per second. 190 meter per second is quite big. So how do you explain this? How do you explain this? You have a theater, it is houseful. It's houseful. The movie is over. You're coming out of the door. Can you come out fast? The space available is suddenly less. So many of you are there. You can't squeeze in and come out. It's going to take more time. Think of a movie which is not very popular. There are just about 20-30 people in the theater. The movie is over. How will they come out of the door? Will they come out faster or slower? Faster. Similarly, here also, what happens is in the case of semiconductor, the number of carriers is small. So the drift velocity will be faster. They are able to travel faster. Whereas in the case of metal, what happens is so many are there. So they are always having these fellows, these lattice fellows are sitting on the way, and they hit each other, they hit against the lattice, and so the movement is slow. Okay. Okay. Now let's go to ohmic material. If I ask you what is Ohm's law, what would you say? Don't look at what is written there and answer. Just tell me what would you say is Ohm's law? Anyone? Tomorrow there is a special class. I hope you know that at 11:30, so that we finish this chapter. Okay, what is Ohm's law? I think I have to call you out. Names only I have to call. Bal Naveen, what is Ohm's law?
Ma'am, it is like current proportional to the voltage applied.
Current proportional to the voltage applied.
Applied.
Okay, good. Okay, so I was thinking that you're going to say V by I equal to R. Good for not saying that. Okay, so now hey, you all know the answers, then why don't you talk in the class? I feel first thing is I'm not able to see you. You can see me, but I'm not able to see you. I can see only my screen. And I don't know any of you personally. So it feels like a blind person talking. And on top of it, you are silent. In front of a blind person, if you are silent, what happens? The blind fellow does not know if somebody is in front. I feel like that now. Okay, so let's look at what are ohmic materials. So I told you that in the case of a metal, I had drawn a picture. I showed that this will be positive ion, positive ion, positive ion kept at regular distances. And then I told you there will be the free electrons would be drifting around. Or first of all, when you don't apply a field, they are simply going to be randomly moving. I told you how they will be randomly moving. Okay, like this, then like this, hitting, then changing direction, hitting, changing direction, or sometimes they hit each other and then change direction. So this is a random motion. Okay, so in conductors, between successive collisions, so that means they will collide against each other and with the lattice. Okay, so between successive collisions with the lattice, the free electrons are accelerated by the application of an electric field. So what happens is you're going to, let us say, apply an electric field. If you apply an electric field like this, what happens is random motion and change of direction is something that is always happening. But what happens is these electrons between two successive collision, what happens is these fellows will drift. They will move like this with a force equal to charge into the field applied. Charge into the field applied. They move in a direction opposite to the direction of the field. Okay, and they hit against a lattice or they hit against another electron, change direction. In changing direction, they may come here. Then again, they start accelerating, they come. This time, maybe they will move this much. Again, they hit and then change direction, they may come here. Then again, they start accelerating. So are you able to see that? They are not able to continuously move against the direction of the electric field. They will drift. Again, it's like playing snake and ladder. Snake and ladder. You feel you're moving 2 steps forward, 3 steps backward. 3 steps forward, 1 step backward. It's like that, So that is the reason why on the whole, when you try to see finally, you will find that there is a small movement in this direction against the direction of electric field. And this small movement, resulting movement, is going to have a drift velocity d. So now I hope you understand why the drift velocity is small. Acceleration is happening every time. Between two collisions, acceleration is happening and it will try to, when you are applying a field, it is trying to move against the field direction. But then immediately there is a collision. Because of the collision, they change direction or maybe move back. Then again accelerate, again move back, again accelerate. So in this process, there is a small movement, a drift happening. That's the reason this is called a drift. A small drift is happening in a direction opposite to the electric field. Okay, and you can see that this drift that you're going to get, the drift velocity that you're going to get is proportional to the negative of the electric field. Larger the field you're applying, larger will be the drift that you are going to get. And it is direction opposite to the electric field, that's why this minus. And you already know that J is equal to minus NEVD. Okay, therefore, instead of VD, we can write J by minus NE proportional to minus E. Or N and E are constant for any given material. So you can simply conclude that J is proportional to E. J is proportional to E. What is J? J is the current density in the metal. And what is E? E is the applied field. So you're finding that the current density you're getting is going to be directly proportional to the field. Or you can write it as an equation as J equal to sigma E. And what is the sigma called? Sigma is called the conductivity. Sigma is called the conductivity of the metal. That is a proportionality constant. And unit will be ohm inverse meter inverse. Okay. And remember that resistivity is the inverse of conductivity. Resistivity will have a unit, ohm meter. Okay. So there are two ways by which you will write Ohm's law. One, you can write it as J equal to sigma E, where sigma is the conductivity. Or you can write E equal to rho J. Okay, in all these cases, you're going to find that the current density and the electric field are directly proportional to each other, and conductivity or resistivity is a constant. It's a constant, and please remember, we are writing it in the form of vector quantities J and E. And remember, these two equations signify your Ohm's law, and these two equations are valid only for isotropic materials. What is the meaning of isotropic? Isotropic means properties of the material are not dependent on the direction. In some metals, what happens, in some materials, you take one direction, in that direction, the property will be different from another direction. So they are called anisotropic materials. But for all isotropic materials, these two equations hold good. And now look at this. J is equal to sigma E, or J is directly proportional to E. Okay. And sigma is a constant of proportionality. It's a constant of proportionality, and therefore you can say that a material is ohmic if the resistivity is independent of the magnitude and direction of the electric field. Rho is a constant. Sigma or rho is a constant. It's a constant that does not depend on what is the field that you are applying. When you apply a larger field, larger is the J. But then the sigma and rho remains a constant. As long as this is happening in a given material, you say that the material is ohmic. Okay? Yes, material is supposed to obey Ohm's law if the resistivity or conductivity is independent of the field that you are applying. It doesn't depend on the magnitude and direction of the field that you are applying. Or it just simply means that current density and electric field are directly proportional to each other. Okay? Now tell me, if this is the case, if I'm going to draw a graph, of field versus current density. Current density is a consequence, field is what you are applying. Field is the action that you have done, and current density is the consequence of what you are doing. Okay, so what kind of a graph do you think you will get? J versus E?
Straight line passing.
A straight line passing through the origin. And what will be the slope? Y equal to mx.
Conductivity.
Conductivity. slope will be conductivity. Okay, and 1 by slope will be resistivity. Okay, so you must remember that as long as for any given material, there will be a range, not for any given material, for a given material, for a range of electric field, if you find that the current density and electric field are directly proportional and the conductivity or resistivity is independent of these values, then you say that the material is ohmic. Okay, now some materials can be ohmic only for certain range of electric field. Like for example, it is ohmic here, and after that, if the graph goes like this, then what do you say? It is ohmic only in this range. Beyond that, you find that the electric field is not directly proportional to the current density. So here it is non-ohmic. Whereas in this range, it is ohmic. Okay. Yeah. Next thing. Let's assume the material is ohmic. Let us take now a wire of the ohmic material having a length L and having an area of cross section A. Let the current that you're passing be I. Current enters, current goes out. And then this current is flowing because of a potential difference that you have applied. Now let us write the equation for resistivity. Resistivity is E by J. You know the relationship between field and potential difference. You know E is equal to delta V by L. Minus sign we are not putting because we are only interested in the magnitude. So delta V by L. And what is J? J is current divided by area of cross section. Or you can write it as delta V by I into A by L. So this is the geometric parameter. A is the area of cross section and L is the length. And delta V is the potential difference you're applying and I is the current that you are passing. Or here, now you can just write this as rho equal to R into A by L, where this R is called the resistance of the metal. R is called the resistance of the metal, R equal to delta V by A and delta V by I. Okay, and from here also comes the relationship that resistance will have the unit ohm and resistivity will have the unit ohm meter. So now you can also talk in terms of resistance about an ohmic material. You can say that if you have a material for which the voltage versus current is going to give a straight line. The voltage you are applying versus current is going to be a straight line. Then you say that such a material is an ohmic material. Like here you see there's a graph given here for an ohmic material. See this. For an ohmic material, you're finding that the voltage you are applying, either positive or negative, the direction doesn't matter. The current values are going to be just the direction of the current will change, but the values will remain the same. You're getting a straight line passing through the origin. This is non-ohmic. And please remember, somebody asks you what is Ohm's law, don't say V by I equal to R. V by I equal to R is not Ohm's law. V by I equal to R is just a definition of resistance. So how do you define resistance? Resistance is change in voltage divided by the current, the resulting current. Okay, so now let us, so you have to remember that resistivity is an inherent property of the metal or semiconductor or whatever. It's an inherent property. You take a small piece, it will have the same resistivity. If you take a big piece, it will have the same resistivity. But when I'm saying small piece, I'm not talking of nano size. Nano means 10 to the power of -9. When it goes to nano, properties will all be different. I'm not talking of nano, I'm talking of the real, what is happening around you. If you take a piece of copper and cut it into a 1 meter block, it will have the same resistivity. If you make it into a 10 meter block, it will have the same resistivity. But resistance will change. And resistance depends on what is the direction across which you are planning to apply the potential difference and see a current. Okay, or in other words, let us do this problem, then you will understand what I am saying. You have a block of iron with dimensions 1.2 into 1.2 into 15. So this is 1.2 into 1.2. That is the area of cross section. And this is 15 centimeter. Now, you are asked to find out what is the resistance of the block measured between the square ends. If I take an ohm meter and put it here, what is the resistance? So what do? I must take this area of cross section as A. I must take the length as L. We have seen the relationship between rho, R, L and A. We have seen rho is equal to R, A by L. Therefore, R equal to rho L by A. So length in this case, length is always the dimension. Length is always a dimension across which you are going to apply the potential difference or across which you are measuring the resistance. That is the length. Okay. So don't simply take length means the longest side. No. Length doesn't mean longest side. Length is simply the dimension between which you are going to measure the resistance or between which you are going to apply the potential difference. Okay, but resistivity is not going to be different. So now substitute, you are getting your resistance as 100 micro ohm. Next, what he is saying is, what is the resistance when you are applying between two opposing rectangular faces? Take the same fellow. Now what you do is, this is going to be one side. This side is going to be one side. Okay, and length is going to be now this. This is going to be the length, and this is going to be the area of cross section. Okay, because you're going to put your ohm meter between these two. So now what is resistance? Let us see. Rho L by A. So area of cross section is what I have marked here. L is just going to be 1.2 centimeters. Convert everything into meter and do it. Look at the resistance. Are you able to see that? So resistance of a material, one thing that in school you study is resistance of a metal depends on what is the size of the metal. Yes, true. Resistivity does not depend on the size. Yes, true. But resistance does not just depend on the size. It also depends on what is the direction in which you are measuring the resistance. Where are you going to put your electrodes of, where are you going to put the terminals of the ohm meter? That will also decide what is the resistance. Okay, and please remember one thing, read this part, this is very important. We assume in each case that the potential difference is applied to the block in such a way that the surfaces between which the resistance is desired is equipotential. That means here, this is an equipotential. Similarly, this is an equipotential. Let this have potential value dA. Let this have potential value dB. There is a potential difference between these two ends. And because this entire plate has same potential and this entire same has another potential which is also the same at every point, then you can assume that the electric field inside is uniform. The electric field from this plate to this plate is uniform. Okay, so this is the premise based on which you are doing all these discussions. Is this point clear, guys? So somebody asks you what is the tell me.
So ma'am, for a semicircular rod, the length would be the diameter, no ma'am, for calculating resistance.
Length will be diameter for calculating resistance. I didn't get
like
you. Which
the endpoint.
You mean the? Can you see this pointer that I'm showing? Can you see my? Are you talking about this picture, the second picture?
No ma'am, if you take a semicircular rod.
Okay. If you are taking a semicircular or circular rod?
Like we bend it into a semicircular shape, ma'am.
You're taking a wire and bending it, huh?
Yes, ma'am.
Bending it, okay. Okay. Bending it, yes. Right, then? Then
So, like, if at all we need to calculate the resistance, that would be the end points, no, ma'am, the distance we need to take.
no, the actual length. It is the actual length, not this distance, it's actual length. Just because you're taking a wire, instead of putting it like this, I may take a wire and twist it like this. Resistance will not change as long as I am measuring between these two surfaces. Which are the two surfaces across which you are measuring is going to be important, and what is the area of cross section is also important. You might keep it in any way you like, it doesn't matter. Have I answered your question?
Yes, ma'am.
Okay. So finally, you have to conclude now that the resistance of any metal depends on the dimension of the metal, and it also, for the same piece of metal, you can have different resistance for the different directions that you are considering for measurement. Resistivity will be the same. Okay, so now let's go to, I just want to quickly do this. Let's go to Ohm's law microscopic view. I have already done it. I've already done it 2 times. I've already discussed this. We have seen that these are all the lattices. I said what happens to free electrons? I said they will move, they will hit against a lattice, keep changing direction. You can see here. Okay, so this is what is randomly going to happen. But what will happen is, because you have applied an electric field, what happens is there will be a net movement in the opposite direction. And that speed is going to be 10 to the power around a few millimeters per second. And this is over and above the thermal velocity, which is 10 to the power 6 meter per second. So between random motions, they collide with the lattice and impurities and lose kinetic energy. That part I didn't tell you. Let me just tell you what is impurity. I gave you the picture of the lattice. Where was that? Oh yeah, I gave you the picture of lattice. What is lattice? Tell me. What is lattice? Lattice are the positive ions fixed to their position. Now, sometimes what happens is no metal will be pure, no material will be pure. Anything that you are going to get in nature is going to be impure. It will have some impurities. Now, what can happen is there can be some carbon or something sitting here. Okay, or there can be some other foreign material sitting here, or a foreign matter will be sitting in the place of a lattice. Okay, so let us see the consequence of that. Okay, so what you have to remember is that because of temperature, because of thermal energy, what will happen is these lattices are okay, or let us say the lattices are there. The lattices are definitely much more bigger than the electron. And then at the wrong place, there will be an impurity also sitting. So what happens is these electrons can collide against the impurity, or they can collide against a lattice. And every time they are colliding, that is a resistance to the free flow of electron. So that is what causes a resistance. Okay, so I hope you know in chemistry you must have studied that by actually adding, like for example, you have a pure metal, you can add some impurity to it. Alloying, for example, will change the property of a material. Have you studied that in chemistry? Brass or bronze, for example, will have a property different from copper. Okay, so when you add impurities, other metals that you're going to change the resistance of the metal, because it's going to increase the number of collisions that are going to happen. Okay, and I must tell you that using the drift velocity, so what happens is you can simply now say that between any 2 successive collisions, you can say that the electric field is going to accelerate the electron with an acceleration A given by E by M. In case you didn't understand what it is, I will tell you. Force acting is mass into acceleration. That is going to be equal to charge into electric field. Or you can say A equal to E by M. So that will be the acceleration between any 2 successive collision. Okay, and let us say the time between, average time between two successive collision is tau. Tau is the mean free time. Mean free time, the time between, average time between two successive collisions. And every time, please remember, whenever there is a collision, it loses energy completely and starts from rest. Starts from rest. You know the equation V is equal to U plus AT. Okay, now imagine every time it loses energy and starts from rest. So velocity, drift velocity is equal to A into T or A into tau, where tau is the average distance between two collisions. Substituting for A, it is E by M into tau. You already know that drift velocity is J by NE. Okay, you can see that you can actually write an expression for the current density as NE square E tau by N. Once more, you're saying that J is proportional to E. Ohm's law, you can get this way also. Okay, and you can see that this N E square tau by M plays the role of J is equal to sigma E. So this plays the role of sigma. Or the reciprocal of this will be rho is equal to M by N E square tau. So you're getting an expression for resistivity in terms of mass of the electron, the number density of electron, charge of electron, and the mean free time. Okay, now I already answered one question. What causes resistance in metal? I said impurity can cause resistance in metal. More about this we'll see in the next class. What causes resistance in metal? How do you increase the resistance of metals, etc. We'll see in the next class. That next class is going to be tomorrow. Tomorrow I have to, under any circumstance, finish this particular chapter. Any doubts?
Yeah.
Okay, so I will stop here. So let me just stop presenting. Stop recording. Okay, you can